Hi everyone, in this video we're going to go through 9b, the rules for differentiation. We're only going to focus on simple terms or simple expressions, basically where we've got a positive power, so n is a positive integer. Okay, so we'll be looking at negative integers later, but we're just looking at simple expressions and finding the derivative of them. For more complicated ones, we do use the chain rule, the product rule, and the quotient rule. So we'll look at them in future videos. All right, so in the second box, basically the derivative of a polynomial function. So if we've got a constant, all right, so let's say you've got f of x equals 2, then its derivative, which we use this notation, f dash x is equal to 0. So we use to denote the derivative f dash x or dy dx. Or it also depends on what variables you're using in the question. So it doesn't have to always be y and x, especially if you're not using y or x. It could be t, it could be n, whatever. But x and y are pretty much the the more popular that you'll see. Okay, so if we've got a multiple, so if you've got if your function f of x has a constant, a multiplier, so let's say you had 2x squared, that 2 remains there, and we're just looking at finding the derivative of the x squared part. All right, so there's an example here. They use 5x squared. So you can see in this example, f of x equals 5x squared. So we keep the 5 there, and we just find the derivative of the x squared component. So your derivative, so f dash x, the 5 remains, and the derivative of x squared becomes 2x. So 5 times 2x, you get 10x. Now, for the sum and the difference, that just means when you've got multiple terms, basically. So if f of x is equal to two terms, gx and hx, then you find the derivative of those two terms separately and you add them together. So if you had f of x equals x squared plus 2x, your derivative, so you find the derivative of x squared, which is 2x, and the derivative of 2x is 2. And then it's the same for the difference. So difference just means you're subtracting now. So f of x equals g of x minus h of x. So your derivative function is the derivative of the first term minus the derivative of the second term. And we've got an example there. All right, so remember I said in the previous video that the gradient of the tangent line is the same as your derivative at that point. Okay, so in example 7, we've got a curve. So we've got a cubic, f of x equals 3x cubed minus 6x squared plus 1. Find the gradient of the tangent line to the curve at this point. So what we need to find is the derivative, which gives us the gradient, and then we substitute the x value into that derivative function. So when we're working out, so we've got the solution here, but I might explain it over here. So we've got f of x equals 3x cubed minus 6x squared plus 1. So the derivative f dash x, so we look at each term separately. So 3x squared, so our power is 3, so that's going to multiply the 3. So 3 times 3 gives you 9. And then we decrease our power by 1. So it becomes a 9x squared. Then the minus 6x squared, the power is 2, so that multiplies the 6. So we've got 12x. And then we decrease the power from 2 to 1. Now we don't tend to write 1 there, so I'm not going to write that. And then we've got a constant term which just becomes 0. So our derivative function is 9x squared minus 12x. Now you use that for any point on your curve to find the gradient. So we call that the gradient function. Now we want to find the gradient at x equals 1. It doesn't matter about that negative 2. We don't really need it to work out the gradient at that point. So we just substitute it in. Now it is a negative. Oh, so it's not a negative. Why did I think it was a negative number? My bad. Anyway, when you're substituting in, I always think it's a good idea to put brackets around what you're substituting in. So 9 times 1 is 9, 12 times 1 is 12, so we end up with a gradient of negative 3. Now, as I said in the previous video, the tangent is a straight line. So what we've found in our equation of the tangent, which is y equals mx plus c, we've just found the gradient, which is -3. So if we wanted to go on and find the equation, we can just substitute in the point 1, -2 to get the value of c. Okay, so we found the gradient, and then we can substitute that point in to get c. All right, moving on to example 12. So before we do that, let's talk about the theory. So an angle associated with the gradient of a curve at a point. So the gradient of a curve at a point is the gradient of the tangent at that point. Okay, so that's what I've just explained. A straight line, the tangent is associated with each point on the curve. So you can actually have infinite number of tangents. If alpha is the angle a straight line makes with the positive direction of the x-axis, then the gradient m of the straight line is equal to tan alpha. That is m equals tan alpha. So alpha is your angle. All right. So if alpha was equal to 135 degrees, then tan of 135 is equal to -1. So your gradient is -1. Now what we've just got here, and this is important to highlight, the angle a straight line makes with the positive direction of the x-axis. So I'm just going to sketch 2 examples. We'll just do 2 axes. All right, so let's say I had my tangent line was like that, and another tangent line is maybe like that. And do a different color. Oh, good. Okay, so we're doing it with the angle the straight line makes with the positive direction of the x-axis. Okay, so that's alpha in there, and this one here is alpha. Okay, so if we're looking at the angle, okay, if it's a positive gradient, that's alpha there, so it's less than 90 degrees. If it's a negative gradient, obviously it's greater than 90 degrees. Okay, so the positive direction of the x-axis. All right, so let's have a look at example number 12. So find the coordinates of the points on the curve with the equation y equals x squared minus 7x plus 8, at which the tangent line, first of all, makes an angle of 45 degrees with the positive direction of the x-axis. So what we've got, let's just do a quick sketch. And I don't know what my tangent's going to look like, so I'm just going to just roughly sketch one. And there's our angle in there. So that's 45 degrees. Okay, so if I wanted to all right, so I want to use the fact that tan alpha, so gradient is equal to tan alpha. So that is equal to tan 45, which is 1. Okay, so I know my gradient is equal to 1. Now we need to find the coordinates of the points on the curve with the equation which the tangent line. Okay, so we need to know, so basically they're working backwards. We're not given a point and we have to find the gradient. We're using the gradient to find the point. All right, so I know that the gradient is equal to 1, but that doesn't tell me much about the point. So what other information can we get to tell us about the gradient? So remember, dy dx or f dash x is another way of finding your gradient. All right, so if I was to take the derivative of our function, which is this one here, I won't rewrite it. So the derivative of x squared is 2x. The derivative of negative 7x is negative 7. And then 8 is 0. So our derivative function is 2x minus 7. So that is also equal to m. So 2x minus 7 is equal to 1. All right, because I've got m equals 1 here. And 2x minus 7 equals m. So the two of them equals m. So 2x minus 7 equals 1. And then we just solve for x. So solving for x, we get 2x equals 8. So x is equal to 4. Now, we've only found the x coordinate. We want to find the whole coordinate. All right, so x and y. So we substitute 4 back into our equation. So not your derivative equation, but into your original. So y is equal to x squared, so 4 squared, minus 7 times 4, plus 8. And I'm going to just do a sneaky look at the answer over here. So it's equal to -4. So the coordinates are 4, -4. All right, so in example 12, we're kind of working back, or not back, I shouldn't say backwards, but instead of being given the point and having to find the gradient, or given a function having to find the gradient at a certain point, we're finding the gradient at a point and working out what that point actually is. So in question B, we've got the tangent line is parallel to the line y equals -2x plus 6. So if lines are parallel, they have the same gradient. So for this one, your gradient is equal to whoops, I hate it when that happens. Go away. M is equal to -2. Now, if it was perpendicular, remember it's the negative reciprocal, so your gradient would be a half. All right, so m equals -2, so we can see that here. We've already done our derivative, so 2x minus 7, so this time we're letting it equal -2, and that gives us an x coordinate of 5 on 2, and then we do the same thing that we did here, but we're now substituting in 5 on 2 instead of 4, so that gives us these coordinates. All right, so basically 2 ways you can find a point using your gradient, or knowledge of a gradient. All right, so I'm just going to skip this into the next page because it kind of flows with the next bit. All right, so increasing and decreasing functions. So your gradient actually tells you a bit of information about what is happening to your function. So if your gradient is greater than 0, so that means it's positive, then your function is strictly increasing. All right, yeah, so think of the tangent at each point. They each have a positive gradient. Now, if f of x is, not f of x, f dash x is less than 0, that means it's negative. So it's a decreasing, so it's strictly decreasing. All right, so you'd have the tangent would have a negative gradient. So gradients of tangents can, of course, be negative or 0. They are not always positive. So at a point on the graph, the gradient, okay, so I'm not going to read all that. So basically, if we're looking at this curve, and we can say, all right, at what point would it be increasing? So I always think if you're a little ant, so here's a little ant, if it's walking up, so it's walking along in the x direction, so it's going up the hill, it's an increasing function, and when it's going down the hill, it's a decreasing function, and when it goes back up, it's an increasing function. So I'm just going to highlight, first of all, where it's increasing. So it's increasing up until B, and then again from A. All right, so the blue sections is where that function is increasing. So for x is less than b, that's the first part I highlighted, your gradient function is positive. It's strictly increasing. And what was the other one? When it's greater than a, so this last part, okay, it is also strictly increasing. Now, the little bit in between, it's decreasing, all right? It's going down, the ant is walking down the hill. So when x is between b and a, it's negative. Your gradient function is negative. It's strictly decreasing. Now, the other two bits of information which are extremely important is this point here and this point here. So basically, at those pink points, your function is neither decreasing or increasing, all right? It is 0, right? So you kind of come to a standstill. So think about you're running up a hill, you get to the top, and then you run down the hill, all right? You're not kind of going to be at a point like that, all right, because that would just be very, very dangerous Okay, but if you're going up a hill like that, obviously at a certain point, you're going to be coming back down the hill. All right, so for x equals b and x equals a, our gradient function is 0, and we actually call them stationary points. It's when you're stationary, it's when you're standing still. Okay, you're not increasing and you're not decreasing. All right, so let's have a look at example 13. So we've got a, kind of looks like a sine function or a cosine function. It doesn't really say what it is though. It could be a quartic. Okay, so we're basically focusing on when we're decreasing and when we're increasing. So I'm going to stick with blue for increasing. So we're going up here is where we're increasing, and we're decreasing down this way, and then decreasing here, and then I'll do pink for our zeros. Okay, so for the first question, it says, when is your gradient positive? When is your gradient greater than 0? So that is between x equals -1 and x equals 5. So you can see here, x is between -1 and x equals 5. Now see, with your inequality sign, it's not equal to, because actually at -1 and at 5, your gradient is 0. You're standing still, or not standing still, sorry, you're not going up or down, you're flat, I guess. For the next one, decreasing. Oops, let me just check that up. All right, so when are you decreasing? So we're decreasing prior to -1, so when x is less than -1, and when x is greater than 5. Excuse me. All right, and then the last part is, when is it 0? All right, so when is your gradient 0? So we've already highlighted it there at 5. Oh, you highlight too much, you can't actually see the number. At x equals 5 and x equals -1. So what we've got here is our set notation. So our elements -1 and 5. All right, so, and it's also not over an interval. All right, so it's just at x equals -1 and x equals 5. All right, so just doing some practice questions. So this should just be revision. Okay, so I'll use the notation dy dx, but sometimes I use f dash x, especially if you've got f of x in the question, not y. Okay, so we've got 3x, so basically your power of x is 1, so we're going to do 1 times 3, which is 3, and then we decrease our power to 0. Now anything to the power of 0 just becomes 1, so your derivative is going to be 3. For b, dy dx, looking at each term separately, so we've got x squared becomes 2x, and minus 3x becomes minus 3. For c, dy dx, so we've got 5x cubed, so 3 times 5 is 15, so 15x squared, and the 3 just becomes 0. And then for question D, we've got a constant there, and remember the derivative of any constant is 0, so we do have to write 0 there. And when you think about that in terms of what the graph looks like, so the graph of y equals 7 goes through like that. So it has a gradient of 0. All right, you can see it's got a gradient of 0. All right, question 2 is pretty much the same thing, but we're just using different notation. I'm going to just skip and do G with you. All right, just because looking at all of them, it's probably the only tricky one. Now, what makes, I suppose it looks tricky, but you should always be looking for ways of making things simpler. So if I look at my numerator, we've got x squared and 4x. So we can take out the common factor of x. So then we're left with x plus 4 over x, and then those x's cancel out. So I'm left with x plus 4. So my derivative is now looking at x plus 4. So the derivative of x is 1. All right, so derivative of the power of x is just x to the power of 1, taking that out the front. So 1x to the power of 0, it's just 1, and the 4 becomes 0 as well. All right. So the next question, decide if these functions are strictly increasing, decreasing, or neither for all values of x. All right, so the first one, it's a parabola. All right, so I know a parabola is both increasing and decreasing, so neither. For 2x minus 4, so that's a straight line with a positive gradient, so it's going to be increasing. And then for negative 2 to the power of x, so I wonder what that would look like. Let's have a look on Desmos. All right, so there's the graph of negative 2 to the power of x. So we've just done exponentials. So you can see there it's decreasing as it's going down. Think about your ant walking along. Now it does look like it's kind of at 0, but it is kind of gradually going down. All right, and then it's got a sharp decline, so it's going to be decreasing. All right, and then we move on to 9C. All right, bye girls.